Imagine you are running a massive generative AI model in a production environment. You need to generate images or data streams for thousands of users simultaneously. For years, the standard approach has been diffusion models. These systems work by slowly removing noise from random data until a clear signal emerges. It is a powerful technique, but it comes with a significant cost. Every single step of that denoising process requires a function evaluation from the neural network. When you stack those steps together, the inference latency becomes a bottleneck. You are waiting for the model to compute, and in high-throughput machine learning operations environments, waiting is expensive. This is where the landscape shifts in the 2026 lecture series from the Massachusetts Institute of Technology. They introduce a framework that fundamentally rethinks how we generate data. Here's the thing about the current state of diffusion models. They rely on stochastic paths. Think of a person walking through a dense forest trying to find the exit. They might wander back and forth, taking detours, retracing steps, and moving in curves. The model learns to reverse this noisy process. It is probabilistic, meaning it relies on randomness to navigate from noise to data. This randomness is what makes it robust, but it also makes it slow. You need many steps to get a high-quality result. The new approach discussed in these lectures establishes flow matching as a unifying framework. It subsumes diffusion models by optimizing for straight-line trajectories rather than stochastic paths. This is a paradigm shift from score-based diffusion to what is known as rectified flow. Now consider this analogy. If diffusion is like walking through a forest, flow matching is like building a highway. Instead of wandering randomly, the model learns a vector field that guides the data point directly from the source to the destination in a straight line. This is not just a theoretical improvement. It translates directly to real-world performance. The curriculum highlights that learned vector fields can generate samples with significantly fewer function evaluations. In the industry, we call this NFE. By reducing the number of steps required to generate a sample, you reduce the time the model spends computing. For a user waiting for an image to render or a simulation to complete, this difference between 10 steps and 100 steps is the difference between a usable tool and a frustrating delay. This brings us to the core metrics for machine learning operations. Inference latency is the most obvious win. If you can get the same quality with fewer steps, you can serve more requests per second with the same hardware. But there is a second factor that is often overlooked: memory footprint. When a model follows a complex, winding stochastic path, it often needs to keep track of intermediate states to ensure the noise reduction is stable. This requires storing more information in the GPU memory during the generation process. A straight-line trajectory simplifies the path. It reduces the complexity of the state tracking required during the sampling process. Consequently, the memory footprint drops. This allows you to run larger models on smaller instances or batch more requests together on the same hardware. In an environment where cloud costs are a primary concern, this efficiency gain is transformative. There is another layer to this story that is becoming critical in 2026. We are seeing a convergence of physics-informed neural networks with flow matching. This is a significant trend. Physics-informed neural networks are designed to model complex dynamical systems where data scarcity has previously hindered generative modeling. By combining them with flow matching, we can model systems that obey physical laws more strictly than standard diffusion models. This enables the modeling of complex dynamical systems where data scarcity previously hindered generative modeling. The lectures reveal that the theoretical distinction between flow matching and diffusion is narrowing, with both frameworks now relying on similar neural ordinary differential equation solvers and loss functions for optimal transport. This means the underlying math is becoming more unified, but the application of straight-line trajectories remains the key differentiator for speed. Think about the implications for deterministic generative AI. The future points towards deterministic generative AI replacing probabilistic sampling in high-stakes domains like computational biology and material science. In these fields, you cannot afford the randomness of standard diffusion. You need reproducibility. You need to know that if you run the simulation twice, you get the same result because the physics are encoded in the flow. The efficiency gains of continuous normalizing flows drive this shift. It is not just about making images faster, it is about making simulations reliable. When you look at the convergence speed, the benefits are equally striking. Because the trajectory is straighter, the model learns to map the data distribution more efficiently during training. The loss functions are optimized for the transport of probability mass along these straight paths. This means the model converges faster during the training phase as well. You spend less time iterating on the neural network weights to achieve a target performance level. In a fast-moving research environment, this speed of convergence allows teams to iterate on their architectures more quickly. They can test new ideas and deploy them to production without waiting for weeks of training time. So, what does this mean for the practitioner? It means the standard pipeline of just throwing more compute at a diffusion model is becoming obsolete. The new standard requires understanding the geometry of the data generation process. You are no longer just managing a noisy denoising process. You are managing a vector field that guides data along optimal paths. This requires a different approach to engineering. You need to optimize for the number of function evaluations. You need to monitor the memory usage during sampling. You need to ensure that the straight line assumption holds for your specific data distribution. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.